Welcome to this lesson again in optics, basically optical instruments, and then the subtopic is calculations involved in compound microscopes. We have a question here. In a compound microscope, an object is placed 1.5 centimeter from the objective of focal length 1.25 centimeter. If the eyepiece has a focal length of 5 centimeter and the final image is formed at the near point, estimate the magnifying power of the microscope. We have a summary of the setup. We have the first lens is an objective. The first lens here is an objective lens, and then the lens next to the eye is the eyepiece. The objective has focal length 1.25 centimeter. Eyepiece has 5 centimeter. So we have a formula here for calculating magnifying power of this instrument as negative D, distance of image for the objective over distance of object for the objective, multiplied by 1 plus D over FE. D is the least distance of distinct vision. D is normally positive 25 centimeters. So we know that 1 over F equals 1 over object distance plus 1 over image distance. This, the first one, is for objective lens system. So we shall have 1 over FO, which is 1.25, equals to 1 over DOO, which is 1.5, plus 1 over D image for the objective. This gives us D image for objective lens as 7.5 centimeters. So after getting it, we can now go ahead and get magnification equal to negative of DIO, which is 7.5, divided by 1.5 multiplied by 1 plus the least distance of distinct vision 25 divided by the focal length of the eyepiece, which is 5. This is going to give us negative 30. So this means that the magnification produced by this image is 30. The negative sign means that the image is inverted. You are welcome. We are still in the topic optics, and this is example 2 dealing with compound microscopes. It reads, a compound microscope consists of 2 converging lenses. The objective and the eyepiece have focal length of 10 millimeters and 20 millimeters respectively. If the object is placed 11 millimeter from the objective lens, the instrument produces an image at infinity. Calculate the separation of the lenses and the magnifying power of the instrument. The summary is the diagram here. The first lens is the objective and the second lens is the eyepiece. Eyepiece because it is near to the eye and forms the final image for the eye. This objective has 10 millimeters in focal length and eyepiece has 20 millimeters. We are given the object distance as 11 millimeters. So according to the formula we have to use for magnification, it is distance for image of the objective divided by distance of the object for the objective. So this is the magnification of the first lens multiplied by the magnification for the second lens. So we shall have to first find the distance of the image for the objective lens from 1 over F equal to 1 over D object plus 1 over D image. So this implies that 1 over 10 millimeters is equal to 1 over 11 plus 1 over D of the image for the objective. So D of the image for the objective is going to give us 110 millimeters. So since the first question says that calculate the separation of the lenses, but again they say that the final image is at infinity. If the image formed by the eyepiece is to be at infinity, it means that the intermediate image has to be at the focal point of the eyepiece. If the final image is to be at infinity, it means that the intermediate image has to be at the focal point of the eyepiece. So here you can see from the diagram that this distance is D of the image for the objective, but that remaining distance is focal length of the eyepiece. So which means that separation of the lenses is the sum of d image for the objective plus d plus the focal length of the eyepiece. So that's going to be 110 plus focal length of the eyepiece, which is 20. This gives us 130 millimeters as the distance. Then we got the last part of the question. Calculate the magnifying power of the lens. We already have the formula and we have everything. Let's feed in. Before maybe we have here the D is the least distance of distinct vision. Since our measurements here are in millimeters, we shall not use 25 centimeters but instead 250 millimeters. So angular magnification is going to be DIO, which is 110 divided by DOO, which is 11, multiplied by 250 millimeters divided by 20, which is the focal length of the eyepiece, and this one is going to give us 125. We didn't put negative here, but if you wish, you would put it there, because negative or plus for magnification may mean the image is inverted or upright, but since we are interested in magnifying power, we want to know how big the image is compared to the object, and it's going to be 125 times bigger. Here's the next example, again in the same topic, which reads a focal length of the objective and eye lens of a compound microscope are 2 centimeters and 6.25 centimeters respectively. The distance between the lenses is 15 centimeters. The first part of the question says, how far from the objective lens will the object be kept to obtain the final image at the near point of the eye? And also we need to find the magnifying power of the lens. For magnifying power, we shall see the formula is there. So let's interpret the question. We have two lenses. The first one is the objective lens and the second one is the eyepiece. Eyepiece because the eye is kept here, so it gives the image, final image for the eye, which is magnified or at infinity. The lenses are 15 centimeters apart. We are not given the object distance, which we have denoted with U today. So again, they say that the final image is formed at the near point. So near point is giving us the final image distance for the eyepiece, and that's the least distance for distinct vision, which is negative 25 centimeters. The final image is virtual. So if we use 1 over F equal to 1 over D object plus 1 over D image, will imply that 1 over F, of course we are starting with the eyepiece, this is 6.25 minus 1 of the image distance. Since it's negative, this is now going to be a plus. 25 is 1 over D, so this is going to be D object for the eyepiece. D object for the eyepiece, using your calculator, is going to be 5 centimeters positive. So this distance DOE is 5 centimeters, yet the total separation is 15 centimeters. It means that the image for the objective is going to be 15 centimeters minus 5 centimeters, which gives 10 centimeters. So it is positive 10, meaning the image is real here. So we have the image distance for the objective. Now we have gone to the objective lens. We can use the lens formula again, 1 over F, which is now 2 centimeters, equals to 1 over U, which is the object distance, plus 1 over image distance, which is 10. So in this case, U is going to become 2.5 plus 2.5 centimeters. So the object should be placed 2.5 centimeters on the left of the objective lens for the final image of this setup to be formed at the near point. For magnifying power, we have a formula here. Magnification is equal to negative D image distance for the objective over object distance for the objective multiplied by 1 plus D over FE. So this first part gives magnification for the objective lens multiplied by the magnification for the eyepiece. We have everything. Let's just feed in. This is going to be negative DIO. So DIO in this case, we got 10 divided by what we have got, 2.5, multiplied by 1 plus least distance of distinctive vision, 25, divided by f of f eyepiece, which is 6.25. So finally we get the magnification as negative. Using the calculator, we get negative 20. The answer now means that negative image is inverted, and then the real magnification is 20, meaning that the image is 20 times bigger than the object. Here's the last part of this question. Where should the object be placed for an identical setup such that the final image is formed at infinity? Calculate also the magnification of the lens. We go back to the concepts and remember that if the final image for the eyepiece is to be formed at infinity, it means that the intermediate image must be formed at the focal point of the eyepiece. Therefore, in this case, to get DIO, it should be the total distance separation between lenses minus FE. This is going to be equal to 15 minus 6.25, which gives us a positive 8.75. Giving us a positive, it means that the intermediate image is a real one, and this intermediate image, even though it's an object for the eyepiece, it is the image for the objective. So now we can use this distance to get the object distance for the first object of the system. Using the lens equation, 1 over f equals to 1 over d object plus 1 over d image. It means that 1 over f, so now we are dealing with the objective lens system, which is going to be 1 over 2 equal to 1 over d object, which we are looking for, plus 1 over 8.75. The object now becomes positive 2.59 centimeters. Positive again means that the object is real, so we should place the object at a distance of 2.59 centimeter from. Now to get the magnification, we use the same formula given here. Magnification is equal to d image for the objective divided by d object for the objective, which is the magnification, linear magnification for the objective lens, multiplied by the d over fe. So we just feed in magnification is going to be DIO, which is 8.75 divided by 2.59 multiplied by least distance of distinctive vision, 25, divided by 6.25. The final answer becomes 13.5. Magnification is 13.5, which means the image is 13.5 times bigger than the object. I hope you have enjoyed the first examples about compound microscope when we are dealing with the two cases, final image at the near point and final image formed at infinity. So here is now your exercise. Try it out. The answers here are 2 and 5 centimeters. Please give me feedback when you try it out. If you get any trouble, feel free to ask me.